All right, thank you everybody for coming over. We had a little pool going in the HPC group of how many people were actually going to show up, given all the wonderful talks that are going on. We all lost. Thank you for coming. So this talk is about high-performance computing. Just do a level set. How many people know Windows has an HPC product? Excellent. How many people know what MPI is? Pretty good. How many people have written an MPI program? Okay, excellent. So my hope is that by the end of this talk, you can go and think about what can I do with an application, my application, if I can speed it up by not 2, 3, 10, but 100x to 1,000x. What new sorts of problems can I solve with this? And also hopefully give you the ammunition to go back to your boss and say, we really need to buy a Windows HPC product. A lot of you already have a farm of servers that do builds or test or raster, rendering, whatever. And some poor guy usually is tasked with, writing scripts and managing and adminning it. If you don't do any parallel programming at all, this product is actually pretty darn good for just managing hundreds or thousands of machines in your enterprise or your HPC setup. So I'm going to be talking about the product a little bit, just that people know what it is. Then we're going to dive into the programming models and show you a couple of cool projects that we're doing. And after that, Jeff Baxter, my esteemed colleague who's a developer working on performance analysis and performance tools, is going to come up and show us how you put actually high performance in high-performance computing. So background in what HPC is. It's referred to as supercomputing, high-performance computing, scientific engineering. It's been the domain of scientists that smash galaxies together to see why we are where we are, all the way down to smashing particles together like they're doing at LHC once they get it back and running, all the way to something in the middle, crashing cars into walls and analyzing the characteristics of the material to make cars safer for us. Tons of different types of simulations and so on that classically have been going on these kinds of cluster setups. The thing that's really hit an inflection point is, as you see in the graph at the bottom, is the price performance. 10 gigaflops for $40 million in 1991. Push forward to 2008, for about $1,000 you can get the same amount of flops on your machine. Recent years, the government actually has sponsored research called HPCS, where they actually try and put a little bit of more productivity into these very expensive systems that they've bought. And this is one of the areas actually Microsoft is putting a lot of calories into to make sure developers, administrators, and people who take care of these systems are very productive. And all the knowledge that you've learned managing Windows systems easily applies here. In terms of verticals that use HPC systems, the classic ones are oil and gas and auto. And you see these two guys on the top right picture. It's not just a pretty picture. That's actually a live engine that's being simulated. And they can go and adjust the little blades. In fact, the second picture on the right, that's from a dam on the river Alba that you can actually go in a cave and turn the little blades a little bit, and then it does a submission of a job to a cluster, and recalculates the fluid flow to help build a better and more efficient turbine, or I don't know what they're called, pump. So the newer scenarios are usually, that we've seen the last 10 years are financial services, bioinformatics, pharma and chemistry, and a lot of energy is going into that. Digital content creation is also very popular, rendering movies, farms of machines out in the back room. But the really new ones, well, but not really new, is like, people are doing project builds and using QA systems for running thousands of different flag combinations on these HPC systems, mainly because it manages the systems very effectively. In fact, the Windows builds people that are doing like 180 applications plus building the Windows code itself, like 50 million lines of code. They're looking into actually doing all that stuff on the Windows HPC system. So what is the product itself? Essentially, it's two parts. You get the Windows server, 2008 as you've seen it, modified a little bit to support the kinds of workloads that we need in the HPC world. And it comes with an HPC pack, which has the typical things you need in a cluster environment, such as a scheduler, a manager, and of course, an SDK to do their programming. Along with that, you also get the message passing interface, MPI, that I'll talk in more detail about. Add those together, you got a pretty nice solution right out of the box. You can press a button, have about 400 or 500 machines under 1 hour, already hooked up, all imaged, ready to submit your first job. Okay. Typical things, attributes of a system like this, system management, storage, data explosion is very important. So we have support for SQL, Unix file servers, a bunch of high-speed file serving systems such as IBM's GPFS, Lustre, and Panasys. Lots of caching for applications that can benefit from that. And a lot of support for programming these effectively and efficiently, such as the neo-RDMA support that I'll talk about. Typical topology for these HPC systems, you have your corporate infrastructure. Usually you have a head node that is the master that manages all the compute nodes behind it, which could be hundreds or thousands. And on the head node, you usually have a direct connection to the corporate infrastructure, and the rest of the system is kind of hidden from that. And there's nothing that says you cannot connect it directly, but the usual setup is that you have a private network for the compute nodes. And if you're doing MPI programming where you need really high-speed, InfiniBand style networks, then you can actually have a separate MPI network set up as well. So with that, let's actually look at the product a little bit, see what it looks like. In the back over here, we've got our roadshow cluster called Bubba, which is about 72 cores, 8 nodes. Actually, these are 64 cores. The product looks like this from a UI perspective. When you bring it up, the first thing you want to do is go through the configuration, which gives you a very nice to-do list and helps you stepwise walk through setting up your cluster. I'll step through one of the wizards. You pick the kind of setup you want, put in a bunch of parameters to set up your private and public network, and eventually, yes, I want to cancel. And so that's the configuration, a ton of options to make sure the setup is to your particular needs and quickly and efficiently done. So for node management, this is where you basically do a bunch of operations on the node. From a top view, you basically see what's going on with your system. You can look at one of the nodes, run a command on it, whatever, and you see the output here. You could do the same thing on multiple nodes. And you group the outputs by nodes. You can essentially take a system, remote desktop into it. And any kind of operation that you would typically want to do, you can just right-click and do. Everything that I talk about in terms of UI, I should say up front, that is available from a command line. We have our own management set of commands, and it's also available through PowerShell syntax and available through a programmatic interface. So continuing on the node state, you basically can look and see what node states we're in. For example, you can take a node and pause it such that it doesn't get assigned any resources in case you want to do updates or anything. If anything's offline, anything's unknown or provisioning, all this stuff during the setup will be reflected accurately. We also have a concept called node groups, where you can actually pick a set of groups. Let's say they have particular GPU cards, or they have special amounts of memory, or a particular setup that you want to directly submit, and when the job manager submits to some cluster nodes, you want to make sure it takes that group. So you can easily do that. Or maybe separate things out by departments or particular needs that you might have. You can also look at the health, in terms of operations, the admins can look at what's been done, archived, committed, etc. Next one, which is the main aspect of this product, is actually job management. Jobs are basically a way of saying to the system, hey, I need about 128 cores and run my job on it. So the system decides, okay, what's available, runs your job on it. If you want to go through the UI, it's a very simple stepwise, give it a job name. You might have a project that you want to specify such that you can look at it per project. You can say how long the job should run. Should it run until it's canceled? If one of the tasks in the job fails, you should kill the whole job. Important for certain types of applications, do you want the scheduling to be done at the core level, at the socket level, where everybody is on the same bus, or at the node level? So you have full control over, depending on your application's communication needs, where things end up. So that's in terms of the job. The job is basically a template for saying what I need and not where necessarily I want it to go all. Task list is where I actually add your tasks. These are the things that I want to add and say, these are the programs I want you to run. Resource selection, if you don't want the job manager to decide all this stuff itself, you can actually go and say, I want these specific nodes picked for me. And then licensing, if you have something that requires FlexLAM or some other licensing mechanism. Okay. Next is diagnostics. Diagnostics, is once you set up a system with 1,000 nodes, mean time between failure, you're guaranteed something's going to go wrong. You need to run something that tells you sanity-wise everything's okay. How are things performing? So we have a whole bunch of diagnostic tests such as ping pong and others that you can check to see make sure the system is healthy. Of course, you've paid a lot of money potentially for a big cluster. You want to know what's going on. So you have a whole bunch of reports that you yourself, an admin or bean counters can look at and say, hey boss, I need 100 more cores with the latest Intel chips or AMD chips, and we got to go get it. So statistics, information, etc. So all in all, is a very nice UI to manage your cluster, both from a developer point of view, from an admin point of view, and there's an easy way to present this to a end user as well. So that's kind of like a quick tour through the product. Let's see, 2 o'clock. I'm going to switch now. Okay, some of these we saw already. I'm going to skip them since the system seems to be up. All right. One thing I didn't show was the heat map. So you can actually, instead of just a list of nodes and their attributes, you can look at your entire cluster, and as the system's executing jobs, you can see how the CPU or other attributes such as paging, et cetera, it looks on the system. We saw this, we saw that. Scheduling. Okay. In terms of syntax for submitting jobs, that's what it looks like. You can say job submit. The head node that I talked about that manages the cluster is class 1. The number of processors I need, 124. If I've created a node group, let's say a node group that has MATLAB engines doing MATLAB-ish calculations, that's what I want it to go to. You can say cores per node, number of nodes you want. You can say all the attributes I said, such as fail on task failure. If one task fails, kill the whole job. If you want some specific nodes, you just name them. If you have an MPI program, which we'll talk about, you can just say job submit, how many processors I need, and execute your MPI task. PowerShell has an equivalent of all these features. Of course, you can pipe it as objects instead of just puny text. So that was the command line. Programmatic interface for C++ and .NET. This is an example of using our scheduler to create a new scheduler. You can say auto-calculate the needs. In this case, I'm doing a parametric sweep. You say the type of it is parametric. You start value, end value, and then you submit the job. I think one thing that's probably worth going back to is the notion of parametric sweep. You don't even have to write any parallel programs to use your cluster if you have a parametric sweep type job, where you've got a program, it's got an input, it's got an output, and it's got built-in support such that you can say task, my input, my output. So you've got something that just pumps through a bunch of files and produces results. That's all you need to do. No parallel programming required. It's a bunch of sequential programs running together. So that's that. Let's go back to the presentation. Okay. So other than command line, programmatic interfaces, and those two, there is also the web interface. We've been working with the Open Grids Forum, which is a standards body, which is, well, I think there's a standards body behind it. But anyway, a group of people that approve what goes in and what doesn't. A whole bunch of top-tier companies that have created what's called the HPC Basic Profile, whereby through web services you can essentially submit jobs, request processors, set some high-level attributes, and I can submit a job on a Linux system, they can submit one on Windows, and vice versa. So a lot of people use this as a web interface into the job manager. It's not as fully detailed with all the specific things you can set up in the full product, but it's the 80% that you need. Okay? So one of the features I hinted at is that we support MPI. MPI is a parallel programming library, which we'll get into some detail later. One of the key things that is available in V2 is Network Direct, which essentially gives you RDMA, whereby you used to use WinSock Direct RDMA and go through some paths in the OS. You completely bypass the kernel and talk directly to the hardware. This is essentially programming and pumping messages through as fast as the hardware and the drivers can support. So Windows as fast as any Linux system out there. Okay? And something important is that this is going to be, we're working with the Windows networking team to actually put this in the full regular Windows releases, so such that other applications can actually take advantage of this. So that kind of gives you an overview of the product. It's a UI that you get. You can submit jobs in multiple ways to it. Now we're going to dive into the parallel programming models that are available. Okay? Parametric sweeps we covered, but now for actually real parallel programming, let me quickly just give you a high-level overview of what's covered in the Windows parallel computing technologies. So there's many ways to slice and dice things. There's local computing at one end where everything runs on a box. There's distributed, cluster, and cloud computing. On the actual forms of parallelization you can, again, cut it in many ways. A typical one is, looking at task concurrency and functional decomposition. One is like data parallel. And these are the typical applications that you might see in each of these zip codes. For all of these parts, we have a whole array of technologies that can be applied to it. Sometimes you might say, okay, that's too many. What do I do? How do I apply these? So we're going to go through some of these so that you know what fits where. I don't know how many people have been to the multi-core talks where they talk about TPL and so on. Excellent. Okay. So any technology that the multi-core team has produced, such as TPL and PPL and so on, can be used at the node level in a cluster. Okay. So it's totally okay to have an MPI program or a parametric sweep program, especially with the scheduling on node, socket, core, etc. Knobs that we have, such that you can actually use an SMP at a node level and take advantage of their programming models. So lower left hand, you see stuff like OpenMP, which is, again, is a standard that a lot of people support, where you just say pragma parallel and parallelize your loop all the way to top right, where you have WCF and workflow and so on. Our technologies are like the MPI and MPI.NET, and we're working, and we already have prototypes of using the TPL technologies that multi-core team has done and applied on a cluster. So instead of saying parallel.4, you say something like metaphoric cluster parallel.4. And instead of just going to 24 cores, you go to about 24,000. Would that be enough? And of course, p-link. You probably saw p-link. Everybody knows what p-link is? Okay, now we're going to do cluster p-link as well, which is, map reduce with a really nice syntax over a large cluster. Exciting stuff. So let's dive into each of these, well, the ones that apply to the cluster. So what is MPI? It's a message passing library. Again, there's a forums body that's been working on this for many years. Microsoft is part of that effort, and you can use it for essentially high-speed parallel programming on a cluster, very much optimized for that type of message passing workloads. It is a portable standard such that if you have systems running Linux and have MPI programs, it's pretty easy to port them forwards and backwards. So keep that in mind. It's not a language, but there are bindings for all the languages. It's not a compiler specification, and it's not a specific product. When would you use it? When you need a portable model. When your workload is kind of irregular and dynamic, you need to do a lot of message passing, and maximum performance. A lot of the collective operations that we'll cover are highly tuned for cluster models. And it is the only model right now that covers multi-core all the way to clusters. So you can write an MPI program that runs on your dev box, 12 procs or whatever, and then you can take the same thing and zap it onto a cluster of 1,200 cores. What has MSMPI, which is our version of MPI, done? We basically have taken an open source MPICH2, which is the standard that a lot of companies use, and then specialize it for their own implementation. We added all the Windows security work to it, a lot of shared memory performance improvements, because the Linux model for threading is a little bit different, and of course we added the network direct stuff that I talked to you about for maximum performance on InfiniBand style networks. And we're a very good citizen of the open source community. We change up, we put our changes back. In fact, our group, I should say, is very open source, very pro open source. In fact, we've done a whole bunch of projects, and we, in fact, insist, if at all possible, that it should be done open source, and I'll talk to you about some of them. So when you execute an MPI program, what does it look like? You basically say MPI exec. This is the program launcher. It's an SPMD model, single program, multiple data. The same exact thing gets spun up on all the cores. And then within the execution body, you are told which rank you are, as in, like, let's say if you start 8 of them, you are rank number 4, you're rank number 5. The tradition is that rank 0 is generally the master rank, and the rest of them are the slaves. So it decides what the rest of them can do or should do. Okay? What do the APIs look like? That's what it is. Initialization, get me the size of how many people were launched, give me my particular rank number, send and receive, and finalize. These are like the 6 basic ones that you need to write a lot of MPI programs. But the API is actually very, very deep. It's about 160 plus APIs in there. And the bread and butter of it is really the collective operations, where you say, send this message to all 10,000 nodes. Tell everybody to do a reduction and put it over here. Okay. General features. Communicators, when you start it up, that's what's called a world communicator. Everybody's in that communicator, but subgroups, let's say you're simulating a car, doing something, it could be a tire group, could be an engine group or whatever, and they can communicate within each other, that's a particular communicator amongst themselves. Point-to-point communication, sends and receives from this rank to that guy over there, and then collective operations whereby you talk to everybody. And then there's buffered mode, synchronous mode, stuff that we won't get into today, but there's plenty of ways to actually, and knobs to make your code go fast. Examples of these, let's say visually, for example, you can see A is the value in rank 0 with a broadcast message where you give it the buffer, how many items, what the data type is, the root, and which communicator, in this case, the world. So it takes value A and zaps it onto all the processors. You say, okay, that's pretty interesting. Show me what it looks like in the real world. So here it is, a video of, if it comes up, Shift F5. So we actually videotaped a broadcast message across 32,000 cores on 1,950 nodes. And in about 20 seconds, first it warmed up, and now pretty soon you should see a broadcast of 1 megabyte message to all the cores, and there it is. Each of those little squares is a node, not a processor. And it can see just the wave actually propagating across as, so green is CPUs at 100%, and lower shades are less than 100%, just like they're waiting for the message or digesting the message. So it's pretty cool. We're joking that we should program MPI to actually play Pong, where each machine is 1 pixel. Very expensive Pong machine. All right. So broadcast, the opposite of that is reduce. That's the API. Send buff, receive buff, where you reduce into how many, what the data type is, integer, real, whatever, what the operation is that you want to apply to the reduction. So visually it looks like this. A, B, and C get reduced into R. The operations that are built in are the ones in the bottom, but importantly, there's also user-defined operations. Okay, so let's look at some programs. I'm going to hope that our cluster is accessible and still recognizes me. Excellent. Let's see, Visual Studio. So let's look at the simplest program for MPI. So basically, the hello world of MPI programming is you initialize your environment. You always finalize it at the end. And here I'm just doing a rank and a size. Tell the world what the size is, ask what the size is, and ask the library what my rank is, and then you just print out something. So, do I have them already built? Yeah. So if I do a rank size, there it is. I can say MPI exec-n 8 rank size. And you see that each one, all of them got started, one of them got zapped as rank 0, and it printed, and all of them are actually printing their rank. But they could have easily said, if my rank is 0, do something different. Okay? In fact, let's look at that. And of course, you have to do a Pi program when you're doing cluster. All right, so here in this case, we've got the classic calculation of pi. What we're doing here is doing a branch inside. So inside the program, I'm saying if my ID is 0, do something different. In this case, ask for input for the number of intervals under the curve that you want to add up to calculate pi. You broadcast the message, in this case, just a few nodes. This is the end at the user input, calculate, and then you get your partial sum for you, and then you do a reduction, and you use the built-in MPI sum reduction. And then you, if it's rank 0, because you don't want everybody to spit out a printf message, right? So let's run that. MPI pi, I think it was called. Okay, so let's say 4 intervals. Okay. 0. Okay, so that's running just on my local box now. Let's say, and you should get a message. Oh, see, I didn't call MPI finalize. Okay. Oh, I think I know what the problem might be. Flush. out. Hopefully this will work. Please work. All right. So let's say, okay, so there it is. It ran 8 copies. It did a broadcast of the n that I input to all the ranks. They all calculated their partial sum, did a reduction, and printed it out. Okay? So that's that. Now next, we're going to go into using .NET for doing parallel programming. So all this work has gone into optimizing MPI for clusters, but here we are pushing .NET, where's the connection? So Doug Greger and Andrew Lumsdale did a fantastic wrapper around MPI library where you can just program in natural .NET C# style and still have all the benefits on all the speed of MPI underneath. What does it look like? Let's take the same Pi program. Where is my C# Pi? Okay, so in this case, you're doing the classic dart throwing. You've got a square, you've got a circle inside of it. You randomly throw darts. If you take the ratio of the darts to the square, adds up to pi. What does it look like? Instead of saying MPI new, init and finalize, you new an MPI dot environment. And of course, you get tooltips for all the APIs. Communicator, in this case, world. That's where all the communication is done through. So you do basically, if my world rank is equal 0, this is the equivalent of my rank in the other program. And then you simply do a world.reduce. Okay? So let me see if I've built this already. C#. Oops, not C shell. Sorry. Oh yeah, I should say that. I just went into C shell. Windows actually comes with a product called SUA subsystem for Unix applications. C shell, Corn shell, compilers, tools, all the 300 utilities you get with Unix and Linux. You can actually do all the stuff that I said and manage your cluster using your favorite Unix shell. No problem. You just go in the Windows install and actually click that you want SUA installed, and you download some SDK, and you've got all this stuff. So let's see. Where were we? Okay, C# Pi. Okay, so I think we can pass it a parameter to, let's say, 1,000. Okay, so then we do, so now let's actually use the job submit instead of just directly doing an MPI exec, so I can set a few other attributes. Okay, so notepad run.bat. Here I am specifying, hey, just set up a path for this job submit. You can specify the standard out, where it goes, standard error, where it goes, how many processors do you want, and all the other attributes, and eventually MPI exec and the name of the program, and we're going to pass it a parameter. Okay? How about $1 billion? Okay, so before I do that, let me bring up the heat map so we can actually look at this as it's being run. So we have multiple ways of looking at heat maps, and I'm just going to bring a different one. Let's see. CD C:health. Run health. Okay, so this basically shows you CPU, paging, etc., priority, etc., all the attributes you can set on your performance analysis tools to see what's going on. So let's run this guy. The job, you see that it's been submitted. It gives you an ID. You can do a view on it. And you see here it's heating up and running, and I'll hit R. I guess, is it R to refresh? Whoa. Okay, sorry about that. Jeff, damn you. His tool. Okay, that was not good. Funny, but all right. 1 second. All right, let's go back. Where were we? Oh yeah, we've got tons of cool tools that in the tool pack that comes with the product that you can essentially play around with a lot of aspects of the product. Okay, so we did that. Oh, last thing I was going to show you as far as programming was F#. And of course, F#, functional language, multi-paradigm language, functional being one of its main attributes, is also available, or just like you have MPI.NET available for Python. Yeah, we have a bunch of Python examples that I didn't include. If you go to Microsoft.com/HPC/dev, you see a whole bunch of tutorials that take you through full scenarios of how to write MPI programs, take an application in any language you want, examples for each language, and it walks you through compiling it, building it, compiling it, running it, debugging it, analyzing it, et cetera, et cetera. And while we're here, I might as well just show you a quick view of this. Let's see where we are. Yeah, we're going to come to it, I guess. Sorry, I'm a bit lost at which machine I was on here. Okay. So how are we doing on time? We good? Okay. I think I'm going to skip the Fluent demo. It seems like we're going to be short on time. Fluent is a major CFD application that runs on Windows HPC. We have a demo of it over at the booth, and you should go take a look at it. Gorgeous graphics. You can simulate a car flying in air, or you can change it to medium H2O and see what the characteristics of the flights are in the water, and has solvers that run and work on the mesh in parallel on the Bubba cluster. If we have time at the end, I'll show it to you, but meanwhile, let's go forward because I think I'm babbling too much. Okay, we covered that, we covered that. Oh, one of our great partners is Alinea, that they've ported their very, very well-respected Unix and Linux debugger onto Windows. So remember all those ranks that I told you? So you download this, goes in as a VSIP plugin, and drives the Visual Studio debugger engine. Here you have all your ranks, in this case 16 of them, and you can select groups or subgroups and create subgroups here, and these could be hundreds, and you can say pause this 50, let the other 50 take one step, hit a barrier for everybody, filter using the VS built-in filtering. Usually when your program starts, there's a whole bunch of other threads that you see in the threads window. It hides all of that complexity away from you and just looks at the ranks in your MPI program. Cool stuff like variable lamination. Show me the value of this variable across all my ranks. You give them some expression. In this case, buff sub 0 is 7 on process 2, and it's 9 on process 0. Of course, this could be a ton of stuff. Like you're debugging, you expect buff sub 0 to be some value across hundreds of ranks, and one of them pops out being different. Instantly groups it for you, and boom, there's your bug. Here is a Boolean expression, in both processors. It's true. Great. That's what you expected. So you can download this product right now. Go to alinea.com. Has a link for Windows. Click on it. You can download it. Collective functions, just to finish those for MPI. A popular operation is scatter, where you get, in process 0 or rank 0, you get A, B, C, D. It maps them on to the first slot in all the processors. Gather is the opposite of that. You've got all these processes that have values here, and just bring them back into process 0. All gather, kind of you see the mapping. A, B, C, D, here goes to A, B, C, D, here, A, B, C, D, here, A, B, C, D. All to all, this is where everybody sends everything they have, and then you can look at the mapping. A0, A1, A2, A3 goes to A1, A0, A1, A2, A3. So a lot of deep, deep, deep APIs that you can use for collective communications, and they have been heavily optimized to take advantage of your particular topology. Are these processes on the same box? Well, yes, let's use shared memory. Are they on the same rank, on the same rack? All reduce take all the values in here and reduce them like this, scan, another operation. Oh yeah, we've already covered C#, but basically it's a very beautiful language for doing MPI programming. This program of telling all the hosts, give me your name, put them in a list, sort them, and print them, would have taken 3 pages of code in raw C. Mainly because when you do an MPI gather, your receive buffer is fixed, and you don't know what the size of these host names are. In C#, MPI.NET, you just say com.gather, the processor name. If I'm rank, there should be a 0 here. I think there is, but you can't see it. And then just call sort and print them out. That's all. It doesn't care what kind of data you pass it, which is a nice segue to saying, how is it that we claim MPI.NET is really suitable for programming? If you wanted to do a send operation, generic, you would have to do something like this. You would hit a serializer. You would have to pin memory and just wait for the garbage collector to be, so that you don't mess it up. What you really want to do is that if you have an MPI data type, you just want to go ahead and pin, tell the GC to hold off, don't rearrange the furniture, and call the really well-optimized MPI send. Otherwise, then you're talking serialization just like you would. In fact, there's been a lot of Java implementations, 4 or 5 as front ends to MPI. All of them have failed. They've never picked up in popularity because of these issues that you just get hit with boxing and serialization. In C#, we can do moral equivalent of that, except you cannot say fixed T* value, address of what you're passing it. So what we do is just do some runtime code generation, some assembly language to actually get that address and then pass it to MPI send. So for that case, if we don't do these optimizations for netpipe, which is one of the MPI typical MPI benchmarks, pumping messages versus size, native C in MPI would get you up here, megabits per second. C#, because you naively serialize Java, whatever, would end up right here. When we do the trick that I told you, C native is up here, blue. C# is up there, which would be any .NET language. And of course, if you hit the serialization path, you're back down here. But again, for your application, this may or may not matter. But at least the programming model is uniform. You can pass send anything, and the right thing will happen. Okay? So that was kind of MPI. It's an industry standard. We have optimized it for Windows. You can port MPI programs. If you're using .NET and you love .NET languages, you can just call the MPI.NET library. And we have full tutorials on how to use it. And that's that. So that's the MPI side of things. Next is the evolving application support in HPC, where traditionally used to do a lot of the simulations, a lot of the hardcore batch-oriented parallel computing, where you submit something, it's a bunch of input files, bunch of output files, you come back 4 hours, 5 hours later, you pick it up. But now we're actually focusing in V2, along with what we did in V1 on interactive applications. So what we've done is basically take the WCF infrastructure and provide you a programming model where you can use services running on compute nodes as a way of getting .NET programs to scale way, way beyond the box. What does it look like? A sequential worker and loop and do work style programming might look like this, from 0 to 100 million do. In our model, you basically get you start a session, you get an endpoint, we hand you that endpoint, and then you get an async callback, all right, where you actually you have a global here that you eventually reduce over. And that's it. Jobs get submitted, and you're just zapping the work onto services that are waiting for your request. Architecturally, it looks like this. You create a session. It submits 2 jobs to the cluster, a broker job that manages the traffic of sending the request to the services, and the actual service job. And then these service instances start up on each of the compute nodes, and you could have 5,000 of these. And after that, the job manager gets out of the way, hands you the endpoint, and from then on, your client just makes WCF calls through this path, through the broker, onto the service. And after that, you're all set. So we have a quick demo to show you this in action, where we have a spreadsheet. We're doing Asian options calculations, where you could do it on a multi-core system, or you can just put it on a HPC cluster of any size. So for that, I'm going to go back to Bubba. Let's see, why do we have so many of these? We need to kill this guy. I see what's going on, sorry. It's on the wrong window again. Agent options, here we go. Okay, so we've used VSTO to actually import a workbook right here. You can just go File, New, use the extension to add a workbook here. We've created a service. Here's a service contract first. Let's look at that, what the API looks like. This is your contract. You're passing it some initial value exercise up and down, interest rate, periods, and runs. The actual service that you execute, this is the code. Here's the API that we had. This is the code that actually gets zapped onto each of the services. And then in the worksheet, let's view that code. This is where your client sets up a job, talks to the HPC scheduler, picks the ranges of what it wants to calculate, and then starts calling the service. Okay. So let's start to see what it looks like. This is here that he submitted the job, told the broker and the service nodes to be ready, and here are the parameters that I'm going to pass to that method. Here's how many Monte Carlo runs I'm going to do, and I hit run, and there it is. So I actually got the values from here and called a whole bunch of, in this case I think I specified 32, but it could be 322, 30,000, whatever. And you get something that would run literally in hours, be part of a return action. So let's say if you got some sort of application that you need to do some serious computation and your client is actually on the phone and you say, let me call you back in a few hours, you can actually do it in real time. And these are the types of interactive applications that this enables. Okay? All right, so we covered that, and we're almost done with the programming models. Okay, so we did that. Message latency is pretty impressive. This is 1.4 milliseconds. Once you actually throw in the broker, it's a little higher, but it's still pretty good. Number of messages per second on a dual code Xeon. It's actually, this is kind of an older slide. It's about 8,000 messages per second right now. These are the high-level messages that you can look at the slides. So far that was to summarize the programming models. There's MPI, MPI.NET, parametric sweeps, and now cluster SOA using the WCF model for much more interactive style and writing primarily in .NET types of applications. And of course, at any node level, you can use TPL, PPL, and all the multi-core technologies. Okay? So a couple of cool projects that we did, given the number of different technologies that we have, how do you make sense out of them? How do you categorize them? How does OpenMP compare to TPL? How does MPI compare to MPI.NET? I want to try it out. So we, with the help from Professor Safonov and his PhD students at the University of St. Petersburg, we took 13 kernels that are referred to as dwarfs, Philip Collella's original 7 and then 4 more, that basically cover a whole spectrum of workloads in the industry. So we took those and said, hey, how about parallelizing these using all the available technologies such that you can play around with them use them as templates to start your own application and see how F# looks versus C++. And then, of course, you need some input files. So we did some input data, small, medium, large, depending how long you want the work to go. Today, we have OpenMP, TPL, MPI, MPI.NET support, and then we'll have these pretty soon. And once you run it, you want to see how they compare. So we plot the results using Excel or JumpShot or Vampire, which are trace visualization applications. And of course, you don't want to run them all the time, all of them at the same time. So you have a driver that can pick and choose which ones you want. And of course, because we are HPC group, we're going to try and release all this stuff very soon as open source, such that you can add your own stuff and hopefully improve these. What are the dwarfs? Here are the classic 7 ones: dense matrix, sparse matrix, spectral, n-body, typical stuff you find in HPC. And then in embedded, these are, red being very popular, yellow being less popular. Spec benchmark, 6 of these benchmarks cover like 70% of spec. Machine learning, games, and then a lot of database-related stuff down here. So it's a pretty wide spectrum. And because we have it for managed and unmanaged, all of these technologies, inputs of different sizes, then you run it, trace it, plot it, analyze it, and so on. Oh, and I forgot to say, hybrid models using MPI with OpenMP. How does that work for structural grid? So you can use it for these types of work, comparing technologies, languages, benchmarking, and so on. These are not necessarily the absolute optimal ways you could program these things. We wanted to get within 10%. It's more for comparing and contrasting the different models. A domain expert could probably come in and do a little one faster that's, squeeze 3 more cycles out of an inner loop. That was not the idea behind it. So the driver kind of looks like this, dwarf bench, names. Oh, actually, we should probably demo this. Let's see, so 237. Okay. Start dwarf bench. Okay, so you can basically say, dwarf bench dash help gives you all the options. Then you can say, I think I have a demo script here. Yeah. So if I say, run dwarf bench, structured grid, what if basically tells me which ones it would pick. It's going to pick structured grid, managed, which means all the .NET stuff, unmanaged, all the C++ stuff, serial version of it, TPL version of it, MPI version of it, hybrid MPI plus TPL, and OpenMP version of it, and so on, and then it would run it. In this case, this one is sparse algebra and dense algebra, very large size inputs, parallel, only run the MPI models and plot them. And let's actually see one of them. So like I said, all this stuff is going to be available on CodePlex, and let me show you some of the code. Okay, so here are all the projects. This is about 14,000 lines of code. Let's pick, structured grid. Everybody knows that. Let's look at the managed version. For managed version, here are all the models: MPI, hybrid, serial, TPL. Let's look at the solver for it, for TPL. So we should be able to do a parallel.4 somewhere. There it is. So there's the implementation. MPI, let's look at that. Here's using MPI.NET, communicator.world.barrier to get everybody to stop at the same place in the code. It would be interesting to look at the unmanaged version of it just quickly. Here's unmanaged. For the hell of it, let's look at, unmanaged, here we go. OpenMP has that. Everybody loves OpenMP. And here's the solver. Oh, here it is. So the same exact kernel of 20 lines of calculation, matrix operation, done using Pragma OpenMP Parallel 4, which does the moral equivalent of TPL's Parallel.4, but a little more statically and doesn't have the work stealing algorithm underneath of it. So it's a great way to compare and contrast all this stuff. And this is running, and hopefully soon it'll give us some results. And we see it gives us a bunch of zeros. I think it was structured grid. Yeah, here it is. And let's break the size down. I think we picked MPI. And we see that MPI.NET is slightly slower than MPI. So if you specify all the models and all the different dwarfs, you can see a very full, nice graph. And you can look at all the data like that. And by the way, this was small input, so really, you need to do a little bit larger to scale them. And of course, Vampire, which is also a very high-end message tracing and analysis and viewing utility coming from Unix world, done by TU Dresden, Wolfgang Nagel and friends. That's also available in Windows, and it's gorgeous on Windows, and Jeff will show you. Here it is. It's actually launching Vampire, and hopefully this will come up quickly. Yeah, so notice that I'm using ETW tracing. So if you're Unix crowd rather, a moral equivalent of dtrace is ETW, and we have a whole bunch of tools built in, such as MPI exec-trace will trace your application, your MPI library, all the way down to the drivers, and you can exactly see when a message was put on a card and when it actually arrived and how much it was in the library versus the application. So meanwhile, I'll go back to, and we'll come back to this when it's ready. Okay. Okay, so what does it look like? Yeah, so you saw the graphs. This is kind of what it looks like. It's good for teaching. It also does XPerf, so you can plot it in XPerf, again, using ETW and analyze exactly what's going on within the code so you can understand the characteristics better. This up here is a jump shot, which is an open source trace viewing utility. On this side, I actually have Vampire, which Jeff will go into more details about. And that was the dwarfs. So basically, 13 kernels, parallelized using all our technologies that we know of, and we're going to continually add to it, will be available on CodePlex. Next, another cool project that we did, and I'll just cover this quickly because we're running out of time, is a game of Go. The UI applied to Surface, which is a very natural environment for it, and ported to Windows HPC cluster. And you say, wait a minute, what do you do with the Windows out? See, the screen resolution is not high enough, so I cannot really demo it. So I encourage you guys to go ahead and stop by the booth and take a chance at beating a Windows HPC cluster running Go. Why Windows HPC and Go? Well, chess is a solved problem. A laptop can beat Kasparov now. You're looking at 30, 40 moves each time for chess. You're looking at 300-400 moves potentially for Go. So in terms of search space is ridiculously large. So a cluster is a very natural way to do a Monte Carlo simulation of trying a whole bunch of games and consulting between the ranks and saying, hey, I've got a winner over here. You guys stop, and then percolating that information up each time a move is made. In fact, the old engines were very complex. Now there's a computer game Olympiad where people bring their best engines, bunch of AI researchers and commercial game vendors, and they play against each other. It's awesome. And there was a guy, David Fortland of Smart Games. He said, hey, I'd like to do this on a cluster. We flew him up. We helped him port his code to MSMPI and optimized it. In fact, Jeff was involved in that. And he entered the World Championships, and he won, which was awesome. He used the Windows HPC. Let me see if I have internet connection. I actually bring up the page. Yes, here it is. Rank number 1, many faces of Go. And it was very interesting as people like matrices, that in this particular championship, many faces beat everybody. Mogo, which is another game from INRIA, France, which we have also available on the cluster, beat everybody else. Lila beat everybody else below it. So you get this very funky, strange-looking outcome matrix, which was... Okay, so... Oh, and I should say that, you really haven't arrived in the high-performance computing world until your cluster ships with a game built in. So this David Fortland guy said he was so happy that we brought him and tuned this code. He said, you know what, I'll give you guys a perpetual free license. You can ship it with the cluster. So if you buy this product, you get the world champion game of Go that you can play against your cluster. Because that's really important to salvage those cycles. And the UI that you see is absolutely gorgeous. You should go and play with it. A lot of detailed attention was put into this, and this was done by Vectorform. And one last plug for a cool demo, if you want to see, is Lab 49's demo that does some portfolio analysis. Again, gorgeous WPF UI and connecting to an HPC cluster. Stop by and see it. And this is just some information on Mogo, which is the other world champion game that we have available on Windows Cluster. So there's a couple of cool projects. I hope to put both of them available in open source, again, once you get past the lawyers. And at this point, I'd like to invite Jeff Baxter, our guru performance analysis developer, to come and talk to you about his magic.
Yeah.
All right.
Thanks, John.
Sure.
Hello? Make sure you can hear me. So I just wanted to do a brief look at some of the performance tools.
This light, and
what I
I'll switch to you.
And what I was going to do was take a fairly simple MPI app, and I chose the Siva Veritosthenes because it didn't have any copyright restrictions because it was written 4,000 years ago. And this is basically where you take a series of numbers. You want to find out how many primes there are less than a billion. So you start with the lowest prime, 2, and you cross off multiples of 2, and then you go to the next prime, 3, and you cross off multiples of 3. And you continue doing that until you've got up to the square root of the maximum number you're looking for, in which case you've covered off all the factors. And then you count up what's not been marked off, and that's the number of primes less than the number. And this is kind of easy to solve. There's sort of an obvious serial implementation, and it's easy to solve if you only want to go look for a billion numbers because you just need a gigabyte of RAM. But if you wanted to say how many primes are there less than a trillion and use this algorithm, that's a bit more complicated because you'll need a terabyte of RAM. In that case, you probably will be using a cluster for it. Now, I got told that I had to use Visual Studio for all of this, but I kind of refused because I figure developing code in Notepad is a little cooler. So, and this is all in C, so I'm just going to walk you briefly through the code. So what I did, I just took this program and parallelized it in a fairly basic way. So we find out how many numbers, what we're trying to find primes up to. We call MPI init. We do a barrier so we can get a common view of time. We start the high-frequency performance counters in Windows, so we start a timer ticking so we can time ourselves. Sean showed you this before. We go off and find out how big the world is and what our rank is within the world. We do a bit of maths to work out. What we're going to do is take this terabyte or billion numbers, and we're going to split it into chunks and give a chunk to each rank. So we work out where where we start in this list of numbers, and we work out how many numbers we have. We malloc ourselves some memory. We have a goto, just to... we zero out all the memory, and then we start the loop where we choose the next prime, we go and find the start of the first multiple of that prime in our block, and we walk along in steps of the prime, crossing off the numbers. So we mark them with a 1 in this case. And then we do an operations where each of the ranks then has to say, okay, what's the next prime that I should be looking at? And in this case, they all basically vote on what the next candidate prime is. And they do that through an all reduce. So everyone decides what their candidate prime is, and they call a min reduction. So they go across all the ranks and they say, who's got the minimum one of these? And that then becomes the next prime that we try for the next iteration. We keep doing that until we've gone through all the primes less than the square root of the maximum number we're looking for, because we know then we've covered off all the factors. And then each of the ranks individually walks through and counts up how many of its numbers, its particular numbers, aren't marked. And then we do a reduce, a sum reduce. So everyone takes their counts, and we sum them all up back to rank 0. We finish our timer, and rank 0 prints out the answer. So I'll compile that. And that's built. And I'm using my dev laptop, so it's all going to be command line, I'm afraid. We'll copy that across to the cluster. And I'll make sure I copied it to the right cluster.
Show them cluster run too if you get a chance. I forgot.
Oh, okay. And now I'm sat on my cluster, and I can run this job. And what I'm doing here is I want to run it on 200. This is one of the clusters back in Redmond. It's a 32-node, 256-core cluster. So I'm saying, hey, let's run on 240 cores. We're going to run over our InfiniBand network, and I'm going to ask it to find me all the prime numbers less than 100 billion. And I run this, and it does the typical sort of high-performance computing thing. It kind of goes off, and you kind of sit there for a while, and you wonder what's going on. And before Sean showed you the heat map, and a sort of just a very basic view of the cluster is somewhat useful for seeing what's happening. So I'll bring up the heat map, and we can see here, this was the Rick-rolling heat map. It's now famous enough that I should use it again. And we can see that all of these nodes are up at 100% CPU, which is kind of interesting, but it doesn't really give us any clue as to whether the performance here is good or what we should be doing in order to improve performance. So what can we do to start looking at this thing properly? So one of the things we can do is we can, and this is something I recorded earlier, we can look at traffic. We do ETW tracing. We have ETW tracing built into our MPI stack, and that allows us to do things like record which rank is sending data to which other ranks, how much data they send, both the size of data and the counts of data.
What are the axes?
And so if you look at this graph, the x-axis is the receiver rank. In this case, this was a 128 rank run. The y-axis is the sender rank.
And what do the different colors mean?
And the colors are, the brighter the color means that there was more amounts of messages were sent between those two ranks. And that's kind of interesting, but 2D, and in the HPC space, 2 dimensions is never really enough to see what's going on. So, obviously you can see this is the same sort of view where we've now flipped it into 3 dimensions. And again, the axes on the bottom, which I haven't drawn, are the sender and receiver rank. And as we go up vertically, this is now seeing that the counts of the number of messages sent between the ranks. And you can see that it's fairly stratified, that we have this sort of layer of data that's passing a fairly high number of messages. We can also view the sort of sizes of data that are passed around, and we can see that the sizes of data are pretty spread out. This isn't a very tightly focused in who it's communicating to. And this is kind of pretty, but again, isn't desperately actionable. You can start thinking about some questions you could answer here. But really what you need is you need some of these more sophisticated and professional tools to get in deeper. And so what we also have is we have Vampire, which is a professional tracing utility, which we have ported across from Unix. And now what I'm going to do is I'm going to ask the cluster to basically trace me one of these executions. And I've done it on a slightly smaller scale. I've just asked it to trace me on 64 cores, so it finishes fairly quickly. And I've just passed to MPI exec the trace all flag. And that's completed. I can have a look at the job output. It's worked out there are 50 million primes less than the number I asked them for, and it took 3.7 seconds. And now what I can do is I can do some post-processing on that so it's able to be viewed in Vampire. Internally, Windows uses ETW tracing. Vampire is an open standard. It uses the open trace format. And so I need to do a little post-processing before we can see what's going on there. So a couple of the utilities we built into the product, one is clock synchronization. Obviously, if you're doing tracing across a number of machines, you can end up in the situation where the clocks are slightly out of sync. And if you've got very low latency communications, so if you can do communications in a microsecond or 1.8 microseconds, which is what we can hit on some of our high-speed interconnects, you need to make sure that those clocks are synchronized before you start trying to do any analysis. So I've run the clock synchronization protocol. I'm now running the conversion. And again, these all run in parallel, so they're fairly fast.
Is it an MPI program itself?
It is an MPI program.
Thanks.
And then I'm going to copy the files onto the head node so we can look at these locally. And if we have a look at what Vampire shows us. So I'll open the trace I just made. Vampire takes a few seconds to process the data. And here at the top, Vampire opens up in a sort of minimalist window. Yellow is application time and blue is MPI time. And you can see that this is one of those typical applications that communication starts to dominate towards the end of the run. And Vampire gives me some pretty interesting views on this data. So for example, this is the same sort of view we saw before where it's sender rank on the top and receiver rank on the bottom. And I can choose many different metrics. At the moment, I'm looking at accumulated message count, but I could look at longest transfer time, the biggest message length. For very large-scale runs where you have hundreds and hundreds of ranks, you can sort of aggregate up and say, let's just group in groups of 4, for example. And zooming in, I can see that there's actually quite a lot of data here. This is counts of messages. So I can see that rank 20 sent 13,000 messages to rank 35. I also get a fairly good view of my application's time breakdown. So here I can say that the majority of the time was spent in application. The yellow bar is application. And then I've got a breakdown of the MPI times. So I spend a certain amount of time doing this all reduce operation. And it looks, in fact, like the all reduce operation is the expensive part of this process. And then I can get a very detailed view on a per rank basis of the breakdown of message time and communication time. And I can drill in as detailed as I want to start looking at what's actually going on in these tens of or hundreds of microseconds. So here I can see I've got an all reduced stage, and I can see if one of my ranks happens to come to it late, or and actually start really answering questions about what I should be doing to improve the performance. Now, it turns out that I chose an example program that is very easy to improve the performance of. It turns out that under very reasonable assumptions, when you do this sieving process, that it is always rank 0 that ends up with the next prime to choose. There's a slide with some maths on, which I won't go through because we're running out of time. But basically, you can assume that the rank 0 will always have the next prime to choose, and so we can remove this all reduce and we can replace it with a broadcast. And I'll quickly do that. So what we do is, instead of everybody trying to decide what the next prime is, we basically just make rank 0 do that. And prime is going to be whatever its index was, plus 2. And then instead of all this fairly complicated code that we had to do an all reduce and to do the voting, I can just replace that with a broadcast from rank 0. And I should buy my notepad. So I'm going to replace this with an MPI broadcast of the prime. We're going to send 1. This is an int64. So I'm going to send 1 int64 from rank 0 to the world. We'll recompile that. And we'll X-copy that across. And if I go and rerun again, I'll do another quick trace. So we'll spin up the same thing again. It's completed. We'll do the same post-processing on it. So we'll clock sync. Takes a little while. We'll convert it to OTF. And it's rather nice being able to use the cluster for these because you can do them all in parallel. So they tend to happen pretty quickly. And we'll copy it all across to the head node again. And now if we spin up Vampire again, For a start, it loads faster. We can see the sort of breakdown of application time to communication time has changed. And if we actually went and benchmarked this, we'd see that actually, in fact, this had executed about 40 to 50% faster. So we have a fairly good set of tools that we can now use to look in great detail into these things.
Excellent. So is Vampire available yet?
It's going to be available. It's coming out in public beta at Supercomputing conference in 3 weeks' time.
3 weeks. Excellent. Excellent. Well, thank you very much, Jeff. This was awesome. So with that, we'll do a couple of conclusion slides and see if people have any questions. So we did that. Get that done. Oh, so since it's a professional developers conference, I wanted to basically say what's available in terms of your virtual Visual Studio HPC edition. In terms of languages and runtimes, you pretty much heard what we have. I've gone a whole talk about HPC without using the F word. What the Fortran compilers still give you is the absolute best, most optimized, loopy floating point code. So if you have number crunching to do and you want the best optimizations, aware of the ISA and chip architecture changes coming out of Intel and AMD, you want to go with PGI and Intel compilers of the world, which nicely snap into Visual Studio. In fact, you can go to Intel and AMD, Intel and PGI, and click, and you get a nicely boxed package that's Visual Studio with their compilers, their debugger, and their project system, tooltips, everything. It's a beautiful Fortran development environment. And of course, we talked about OpenMP MPI, team development, all the usual stuff you get out of VSTS. In terms of partners, we have a ton. All the top utilities coming out of Linux and Unix world, they're rushing to port all of these over to Windows. Math libraries, a whole bunch of them, visual numerics, NAG, Intel's and AMD's libraries, ton of open source stuff, and stuff like MATLAB and Mathematica and Maple. Not only they're available on Windows, they have direct connections to Windows HPC, where something that takes 4 hours, you can actually zap it onto a cluster and see it in 4 minutes. It's beautiful. And .NET, we talked about that, and ID, pretty much what it is. One thing I didn't cover as much, if you want to come to the booth, I'll talk about parallel debugging. We have an MPI debugger built into Visual Studio, and of course, you've got the Alinea add-in that gives you the next level of ease of parallel program debugging. So we kind of covered multi-core a little bit. We covered the cluster technologies. One area that we're looking at and investing a lot of calories in is actually bringing a lot of these different programming models, some of which were standards that we have to obviously move forward. But how can we make all this stuff be a little bit more palatable for people? You really want to run your application once. If it's a typical parallel.4 thing, and easily zap it onto a GPU, a multi-core box, and a cluster. Just like you don't say register int I anymore, register allocators are a lot smarter these days. You shouldn't have to go and mechanically do all these changes to make your program run on different types of architectures. So we're going to spend a lot of work on that such that you can use your investment across generations of architectures and different types of architectures. So with that, we have a whole bunch of URLs that you can take a look at, educational stuff, partner stuff, and I will open it. Oh yeah, this was our first PDC presentation. Sorry if we mumbled through a lot of stuff. We hope to come back next year and do a longer talk and have a better booth. And we have a Cray CX1. You must come see that box. It's a prototype box, 64 cores. InfiniBand, and you're going to be able to order it in about 2 weeks or so. It's about yay big, about this high, active noise cancellation system, your own 64-core cluster right by your desk. It's beautiful.
The one we have there hasn't got active noise cancellation. I should warn you already. It sounds like an aeroplane.
Yes. And with that, I'd like to open it to QA. Question?
Quick question. You didn't mention how all this ties back to the cloud.
Yes. So in fact, we've been working with the cloud folks and our own mini cloud. We live in Seattle, so it's got to be something with cloud there. We actually have a cluster out there in the cloud that a whole bunch of universities are using for submitting jobs. Economics professors and students are using them to use that web interface that I talked about, and they submit all these simulation jobs through. So we've been experimenting with the idea, and we're trying to figure out how all this stuff fits together. Some people want to do a mini cloud for their enterprise, and they're looking at HPC. Other people are looking at the stuff that you saw mentioned today, and Google and Amazon style things. And we're working together to see how you can use some of our programming models out there and use some of our technologies as a mini cloud within your own organization. So it's an evolving problem that we're looking at, and hopefully we have more answers for you, early next year. Okay. Next question.
How many nodes have you tested the Windows HPC cluster with in terms of the management infrastructure and all of that? Do you know what the scalability potential is?
So out of the box, 256, no problem. 512, pretty good. When you get into the thousands, you need to do some things a little bit more carefully. When you want to image a cluster, you don't want to just say zap everybody. You kind of want to do it in parts. In the UI, sometimes we've seen some things not scale as well when you're talking 32,000 cores, but those are oddball, number of things. In the sweet spot for enterprise and department level stuff, no problem. And every release, this is our second release. Every release, we're working heavily to make sure we hit the sweet spots very, very nicely. And the V2 version of the product, which RTM 3 weeks ago, is perfectly fine for typical usage.
I would say 256 out the box. If you want to go to 1,000, we're kind of comfortable on 1,000 nodes, but you're going to want to do things like put a couple of hard disks on your head node. There will be higher I/O rates.
Yeah. We also didn't talk about failover on the head node. So you have something, mission critical stuff. You don't have to have just one head node. You can actually have a failover node that automatically things get rerouted if the problem comes up with it.
But all the communication comes back to that head node then?
Correct.
Okay.
Yes.
Thanks.
Next question.
No more questions.
Excellent. Well, thank you very much.
Great. Thank you.
Appreciate your time.